notion towards conic stability. So here, if f is f with complex coefficient is stable if it has no roots in the upper half plane. So we can redefine this definition of stability, saying that f is stable if and only if this set intersection with positive orthant is empty. Now, what is this set? This set is a set of vectors of imaginary parts of roots of f. So, first time it was observed by Jurgens, Theobald, and Wolf, and they asked themselves that whether this can be generalized, because we see here there are two objects. One of them is cone, and other one is the set which we call imaginary projection of a polynomial. So let's look at the imaginary projection of polynomials, the set. This is the set of vectors of imaginary parts of roots of a polynomial f. We call this imaginary projection because there is an underlying projection which maps from r to the power 2n to rn. And here is one example of a imaginary projection of polynomial this. An idea of computing imaginary projection, briefly, we have to extract a real part of polynomial and imaginary part of polynomial, this. And then we need to compute the range of y such that the polynomial in xi will have real solution. And if you do that, we see the nice picture which says that outer part of this circle provides us the imaginary projection of this polynomial. And instead of +1, if we choose here -1, which represents the conic ellipse or circle, then we'll have the imaginary projection as entire plane, Rn. If we are drawing, then in a plane, entire plane. Now, this is another example which shows us that imaginary projections of hyperbolic conic sections, it gives us hyperbolic conic section. So here we conclude some properties of imaginary projection. It is a semi-algebraic set, as it can be thought of as the projection of a real algebraic variety. It is not always closed. It is always unbounded for n greater equal to 2. And if the polynomial is irreducible, then, the map, initial projection is always connected because the map is continuous. Map 1. Oops. This is the map 1. And Jurgens, Theobald, Wolf, they have also observed that components of the complement, they are always convex and finite in number. And this complement of imaginary projection, they have a crucial part in conic stability. Here is another motivation comes from the theory of amoebas, where people are interested to study the logarithmic images of complex variety for, in general, Laura polynomial. And in our setup, we are interested to look at imaginary projection. One can look at real projection as well, but it gives the same result. And if we stick to imaginary projection, then we can relate the results which are already known for stable polynomials. So now we are ready to define the notion of conic stability. So we can choose a proper cone. By proper, I mean full dimensional closed pointed cone. A multivariate polynomial f with complex coefficient is called conic stable if its imaginary projection of that polynomial has empty intersection with the interior of the cone K. Similarly, we can recall the definition of stability here. If we'll assume the cone as the non-negative orthogon cone. Here are some examples, like we can define PSD stable polynomials. If we consider the cone as the cone of positive semi-definite matrix, then we will get PSD stable polynomial when the variable are symmetric matrix variable. And one can define PSD stability with complex coefficient with respect to Seigel upper half space. And here is another class of polynomials, determinantal polynomials, which generate conic stability. And this is already known due to Borsier and Brandon that determinantal polynomial is real stable or the zero polynomial if the coefficient matrices AJ are positive semi-definite and A0, this is Hermitian. And in our setup, we'll see there is a larger class of determinantal polynomials which will be conic stable polynomials, even though they need not be stable polynomials. Naturally, some question arise here whether the class of stable polynomials is contained inside the class of PSD stable polynomials. Answer is no, not necessarily. Not all stable polynomials are PSD stable. Here is one example. And not only determinantal condition is not necessary condition for a stable polynomial to be PSD stable polynomial. So this is one example, determinantal polynomial, which is not stable but PSD. Then we ask that whether determinantal condition is a necessary condition for a polynomial to be PSD. That also turns out to be wrong. Not all determinantal polynomials are PSD stable. Here is one example. Now let's look at hyperbolic polynomial. F with real coefficient, it's a homogeneous polynomial. F is called hyperbolic with respect to direction E. If E is not a zero, and as we have seen that univariate polynomial, this should have all roots real roots. If we have a hyperbolic polynomial, then there is always a hyperbolicity cone associated with it, which says the set of points for which the univariate polynomial will have always negative roots. And it is also known due to girding that this hyperbolicity cone is open and convex. Then in this direction, a remarkable result proved that hyperbolicity cones of F coincide with the complement components of IF. Complement components of IF. And using this, we can say that hyperbolic polynomial is always conic stable with respect to this cone, hyperbolicity cone. So for a hyperbolic polynomial to be conic stable, there are equivalent condition like F is hyperbolic with respect to every point in interior of the cone K. And another equivalent condition says that interior K should be contained inside hyperbolicity cone with respect to some direction E. I need to define one technical term like initial form of F denoted by in F. It's the sum of the terms of F with multi-degree D, if the polynomial has degree D. That's what it means. So then our first observation was that if we start with a degree D polynomial, which is determinantal, and its coefficient matrices are Hermitian matrices, and we know there exists one direction E. Along that direction, the span of the coefficient matrices is positive definite, then we can say that initial of F is hyperbolic, which is very straightforward. And second, every hyperbolicity cone of initial of F is contained inside the complement of imaginary projection of F. And here is the idea of the proof. So maybe I'll skip due to the time constraint. So let's go to quadratic polynomials. Our next result, we actually derive one well-known result, which says that hyperbolicity cones are hyperbolicity cones defined by quadratic polynomials. They are always spectrahedral. And we prove that if we start with a quadratic polynomial F, where the matrix representation A has n-1 positive eigenvalue and 1 negative eigenvalue, then there exists one linear form L such that this will have a determinantal representation. And we have a recipe to generate this L of Z, linear form L. This theorem is based on three steps. First, we realize that any quadratic form in real quadratic, they can be classified into one of these three normal forms. Then one of these normal forms. You are using. So then we compute the imaginary projection of the polynomial, which turns out to be the open Lorentz cone. This is in plane, it looks like this ice cream cone. And then third one, we use the fact that open Lorentz cone has spectrahedral representation. And note that the initial of G, which is the normal form of F, using standard for reduction formula, we can get this normal form from starting with the F like this. Then use this classification and find the initial projection of F, which has two unbounded conic components, which are actually open Lorentz cone and it's negative. And also knowing the fact that they have spectrahedral representation, we can generate this L linear form. Here, it gives us one key idea to lead to our main result of this paper. It says that we observe that if we have spectral representation for the cone K and the conic components of complement of imaginary projection of F, then we can translate this conic stability problem into a problem of spectrahedral containment. That means we need to see whether this is, if both of them has spectrahedral representation, so it turns out to be checking spectrahedral containment in order to check whether polynomial F is conic stable or not. And non-negative orthon, they have spectrahedral representation. Positive semidefinite cone, they also do have spectrahedral representation associated with the linear matrix polynomial of this form, where jth entry is 1 and rest of the entries are zeros. And in this case, it's just, we can think of half of EI EJ transpose plus EJ EI transpose. These are the matrices. And EI is a standard vector. So we do have spectral representation for non-negative orthon as well as positive semidefinite cone. We use that fact, and using this setup, like we can write a spectrahedra. Suppose we have linear matrix pencil UX and VX, and that generates this spectrahedra SU and SP. Then we can define a linear map from the space of curly U to V, which maps which maps positive semidefinite matrix from curly U to positive semidefinite matrix to curly V. So it's a positive map. And then we used this well-known result about spectra heterocontainment. It says that this positive map is, this linear map is positive if and only if corresponding spectra hedra is one of them is contained inside other one. It has another known fact that it is associated with one semi-definite feasibility problem, which says that there should exist one positive semi-definite matrix, and the coefficient matrix VP, which is associated with this spectrahedra, they can be always represented as linear combination of matrix pencil associated with SU. But this only provides sufficient condition. So here, using this fact, we derive our main result, which also provides sufficient criteria for a polynomial to be conic stable. It says that if we start with a determinantal polynomial whose coefficient matrices are Hermitian, then and we have these two conditions: initial of f is irreducible and it is hyperbolic, and also we know the cone K has spectrahedral representation, which is this. Then theorem claims that if there exists a Hermitian block matrix C, which is also known as Choi matrix, it's a block matrix, this C and with this combination, then always F is K stable or conic stable. And this theorem is mainly based on the fact that we can always write hyperbolicity cone associated with initial F, which is denoted as this, which would give this form, this linear matrix pencil, that can be written as heteroidal product of Mx, which is the spectrahedron linear matrix pencil associated with the spectrahedral representation of the cone K and the Choi matrix C. So now it turns out that we have to decide whether such a matrix, block matrix C, exists or not, and which is a semi-definite feasibility problem. Then here it's like we can see as a special case, it gives us the well-known result which I mentioned before, the determinantal polynomial due to Borsia-Brandon. Determinantal polynomial is real stable if and only if the coefficient matrix associated with this, they are positive semi-definite, because we can view the Choi matrix as a block diagonal matrix whose non-diagonal blocks are zeros. Then the condition here 4 gives us this condition, which says that each coefficient matrix AJ has to be positive semi-definite. Here is one example of determinantal representation. We knew that, and then we found the Choi matrix, which proves that this is actually a conic stable polynomial. And here another fact is that we can use this result reversely, like if we know there exists a Choi matrix and the polynomial is conic stable, somehow we know this matrix by checking or by solving a semi-definite programming. Then from this we can compute the determinantal representation of quadratic polynomials. This results only so far we have been able to prove for quadratic polynomials. As you can see, this block 4, 1, 1, 8. And here are some open problems. Actually, this is a new topic. There are lots of things to be done. Characterization, it's not yet complete. We have so far given one sufficient condition, and that too based on if the cone And in complement of imaginary projection, they have spectrahedral representation, closure property, I mean operations which preserve conic stability, that is still open, and whether there is any connection with log concave polynomials or not, that part is not yet clear. We didn't get much time to solve this part. And another thing is we are hoping that if someone can generalize hyperbolic programming using conic stability, conic stable polynomials and their associated their cone. Thank you for your attention. Here I will stop. And if you have any question, I can.
Thanks, Papri. Any questions? So do you think there's a nice characterization of PSD stability preservers?
We hope so. It's not yet done in our paper. And Thurston is also here, I hope. So please, if you have any question, please ask us.
So maybe let me mention on these stability preservers, because there was this question. I mean, there are many kinds of preservers, and of course, some simple natural ones generalize, so it's clear that they do not generalize, but of course, there are, I would agree with that, what Papri said, that many of these questions are still open. So.
So it seems somehow like Mario mentioned this conjecture of Tunstall, which was that if you take a hyperbolic polynomial, if you take a hyperbolic polynomial and then you can look at okay, so his talk was about given I guess a cone, you can define the set of matrices with eigenvalues in that cone. And if that cone is hyperbolic, then the set of such matrices is a cone, which is again a hyperbolicity cone. Right?
Yeah. That is
so that's like a purely geometric statement. And what you're doing seems to be like something like that, but at the level of the polynomials. Or I mean, is there not some relation between these things?
Thorsten, if you have anything, you can say it. Because right now, on top of my head, I don't know how to connect them, but I would be interested to see any connection between them.
So of course I can comment from my side. I did not see Mario's talk, but just I mean saw the abstract and so on. I mean, of course, whenever it comes to hyperbolic polynomials, there's this connection, natural connection towards conic stability. I mean, there are slight differences in the model because I mean, in the stability business, one also allows non-homogeneous polynomials and so on. But generally, I mean, it's something like some kind of a sharpening of the hyperbolicity notion, because in the conic stability viewpoint, one kind of asks what kind of cone is contained inside the hyperbolicity cone. This is how you can view it geometrically. So therefore, whenever it comes to hyperbolic polynomials, you might ask the more precise question with respect to what kind of cones are really inside. So therefore, there is a natural connection towards Mario's investigations.
Mhm. I see. Okay, yeah, that makes. So you're looking at, you want basically the difference here is you're looking at this imaginary projection, and then you're I mean.
Yes, so this is something like a more extensive, a more comprehensive view on all the hyperbolic business, and it gives you kind of more information, I would say, and of course, yeah, it's interesting to study these refined views.